We do need to talk about this phase diagram, all right? This pressure versus temperature diagram is called a phase diagram, and it shows you all the states of matter for the particular material that you're looking at. You can see here don't use that over there. You can see here we have the solid liquid line. I'm sorry, the solid vapor line. So maybe let's identify the pieces first. Let's do that. In places where we have high pressure and low temperature, we have the solid. In places where we have low pressure and high temperature, we have the gas. Okay? In between, we have the liquid. There's this thing called the triple point. It's kind of like a critical point. It is a place where the solid, the liquid, and the gas all coexist at the same time. So if we're at that, and for water, it happens to be 4.58 millimeters of mercury, so that's very low pressure, and 0.01 degrees C, right? So right at roughly the freezing point, and 4.5 millimeters of mercury, you can have ice crystals floating in water with gas above, and it would stay that way forever, okay? I killed it. There we go. So that is what the triple point means, 3 phases coexisting, okay? We have that coexistence curve between the solid and the gas, and that ends at the triple point. Any temperature below, or any pressure below, the triple point, as we increase the temperature, we do sublimation, right? We go from solid to gas. So if our pressure is below the triple point pressure and we heat it up, that's sublimation. Once we get to a pressure above, then we go solid to liquid, right? Then it's melting. All right, so we have this line here. This red line that you see starts at the triple point and goes up. This is the line between solid and liquid. This is the coexistence curve for the solid and liquid. That's given by delta H, a fusion as a function of temperature. Water is different than most every other thing you'll ever see. Water's line slopes to the left, right? It's got a negative slope to it. Looks like that. Almost everything else in the world that you see will look like that. The line points toward the thing that is less dense, right? Ice is less dense than water. Ice floats. The line points toward the solid, toward the ice, okay? Most everything else, the liquid is less dense than the solid, and the line points in the other direction. And then we have the curve that we talked about before that goes from the triple point to the critical point, and that is the liquid vapor coexistence curve that we can define by the Clausius-Clapeyron equation. Take a look at this intersection here. Where the liquid vapor line intersects 1 atmosphere, that's the normal boiling point. We talked about that one already, right? Where the vapor pressure equals 1 atmosphere, normal boiling point. Where the solid liquid line interacts with 1 atmosphere, that's the melting point or the freezing point, however you want to look at it, right? So where that line intersects 1 atmosphere, that's the temperature at which you freeze or melt. So we base those temperatures, the freezing point and the boiling point, on where these lines, these coexistence curves, intersect atmospheric pressure. So what we want you to be able to do is recreate one of these phase diagrams, right? If we give you something that looks like this on a test, we want you to be able to label solid, gas, liquid, triple point, critical point, supercritical fluid, identify what the transition is for melting, what the transition is for sublimation, all those possible things, right? So if we give you something that looks like here's a point A, here's a point B, what's the process that's occurring between point A and point B? In this case, it's melting, right? We want you to be able to do those things, right? We want you to understand these things. Yeah, 73 atmospheres is the pressure we got to get to. And we got to get to about room temperature. That's why they use it, right? So it's a little bit warmer than room temperature, but you got to pressurize it to 73 atmospheres. So what is that in PSI? 1 atmosphere is 14.7 PSI. So 14.7 times 73, I don't think your air compressor at home will get there. Triple point you can do. You can do that. The triple point for CO2 is 5 atmospheres. So we actually have to pressurize CO2 in order to get to the triple point. That's why dry ice does what it does, right? It goes from solid to gas because the triple point is higher than atmospheric pressure. So that's why we see that direct conversion from solid to gas. The same thing with iodine, right? I told you iodine goes from solid to gas. Same situation. If you looked at a phase diagram for it, its triple point would be higher than room temperature or room pressure, atmospheric pressure.